this video is basically going to go over chapter 1, but not as a whole. I'm not going to go in depth to like every subtopic. I am going to go through what I remember and what teacher has emphasized a lot on. Also, you can see that my voice is a little bit less loud because I am trying to save my voice since Puasa is coming in a few days. And I also want to practice talking in a way that it wouldn't strain my voice that much because I get thirsty a lot. And again, since it's Puasa this week, I don't want to end up losing my voice because I can't drink water to regain my thirst. So I took pictures of some stuff. Now this chart here, this thing is very important because this is involved in electrolysis and also chemical cell. If I'm electrolysis and chemical cell. And why is that so? Because when you have, first of all, you want to decide which sometimes you don't decide which is your anode, which is your cathode. And then secondly, the main part is if you have multiple ions going to the anode or going to the cathode, you want to distinguish which one is the chosen electrolytic cell, which one is the chosen electrolyte to be used in electrolysis. So like for example, let me see if I can think of one example. Again, I'm going through this blindly. I forgot the exact way. I forgot the exact question, but if not, I have my book next to me. So let's say you have a cell here, right? Let's say you have a cell here, and then simply put the like, let's say this is carbon electrode, carbon, this is carbon, this is also carbon, and then it is electrolytic cell. So you see the longer part represents positive. So the thing about electrolytic cell, this is electrolytic, is that the positive terminal is connected to the anode. So this has to be your anode. The negative terminal is going to be your cathode. So take that in mind. Now if I have a solution, and I want to electrolyze copper to, let me see, copper 2 chloride. I believe that's the most common one. Let me see, if I remember correctly. Yeah, I believe it should be copper 2 chloride because it's one of the more common questions. Let me I'm gonna double check just in case I got it wrong. I used the wrong salt. Copper chloride can be used. So first of all, you must remember that whatever happens in the anode is going to be oxidation, because remember we're still talking about redox. So redox, this is reduction, this is oxidation. So a reaction that involves both oxidation and reduction is considered as a redox reaction. So since electrolysis involves oxidation and reduction, it is also a redox reaction. But that's going a bit more off topic. And oxidation is always going to happen at the anode, and reduction is always going to happen at the cathode. So in their ionized form, we have Cu2 plus and Cl minus. So of course, this is forgot one thing. You are using an aqueous solution. So if you have aqueous copper chloride, wouldn't aqueous mean there's also water? So you will also have H plus ions and also OH minus. So you will have 4 ions suspended in your liquid. You have H, you have Cu, H plus, Cu2 plus, you have OH minus, and also Cl minus. Now, now's the hard part. Where do these go, and what comes out of this cell. That's what we're going to find out. So when you go when these positive ions go to the cathode, for example Cu2 plus, and then you want to turn it into copper, right? Because it's already in ionic form, so you want to turn it into a solid form. So if you want to turn it into solid form, you have to add 2 electrons. Since you're gaining electrons, this is reduced. So this is going to happen at the cathode. So this one goes to the cathode, this one goes to the cathode, and then this one goes to the anode, this one goes to the anode. The second part is knowing which one gets chosen. So at the cathode, you have 2 ions, H plus ion and Cu2 plus ion. Which one is going to become oxidized? To become reduced, I mean. Now, that's when you have to look at this very important chart here. If you look at the thing after that, the electrolyte has to undergo reduction. So we want to look at the part which it says reduction. Okay. This is an example. I'm gonna go to the after that if I can. I think it's here. Okay. So we're gonna find the one that is easier to undergo reduction. So we want a more positive or less negative E0 value or centered electron potential. So we want to go back. I forgot how to go back. Okay, I'm just gonna go out and then go back into here. So wait, let me just remind you again. It has to be more positive or less negative. So easier for it to undergo reduction. When we need to talk about reduction here because these things are happening at the cathode and reduction always happens at the cathode. So with that in mind, I'm gonna mark out where copper 2 ions are and where hydrogen ions are. You see that copper is plus 0.34 and hydrogen is 0. Hydrogen is exactly 0. Copper is 0.34 plus 0.34. So we want to find the more positive one. The more positive one is copper 2 ions. So what that means is at the cell here, copper 2 ions will undergo electrolysis. The hydrogen will not be affected much. It's the copper that mainly reacts with the cathode. So at the cathode, H plus doesn't happen. Cu2 plus gets chosen. So the reaction of that is the ionic equation. Make sure you know your ionic equations are. In SPM, they don't really care about states of matter. Now, anode is where things get very, very, very interesting. Because you need to consider 3 factors. And they come in this order. So it's A or B and then C. A. Is it a halide? If it is, then we're going to find out the concentration of halide. B. Is it an no, this is B. A is it an active electrode? So we need to consider, is it an active electrode, and then is it a halide, and if it's a halide, how concentrated it is, and then C, what is its E0 value? So anode, is it an active electrode? I mentioned just now that we're talking about carbon electrodes here. So since we're talking about carbon electrodes, hence this is fine. That means it's still OH or OH minus or H plus or Cl minus. But if, let's say for example, this is a copper electrode, because copper electrode is the most common one. If it is a copper electrode, what will happen here? Not this, but pure copper will react. What happens is the copper reacts itself. At the anode, the copper electrode itself is the one that is oxidizing. So what happens is the strip thickens, but the strip becomes thinner. But I'm gonna mention more about that later. Now back to here. We're talking about carbon electrodes here. So next, Is it a halide? If it's a halide, what is the concentration of that halide? What is the molarity? So let's see. We have OH minus and Cl minus. Halides are halogen ions. Halogens include fluorine, chlorine, bromine, iodine, and so on. We know that chloride ion is a halide. So we need to take B into consideration. What is the concentration of the halide? Now, I did not give the concentration of this halide. So I need to I'm going to teach you, I'm going to show you what happens if it is a low concentration and if it's a high concentration. The unit is in mole per dm cube, I think, if I remember correctly. Mole per dm cube. So if the concentration is low, then let's see. I actually marked it down here in this thing. This is fancy word for E0 value, which is cathode find the more positive, anode find the more negative. That's what but then at the anode for concentration, if it's a halide, then you have to consider this factor. Halide ions with a high concentration in the electrolytes will be discharged at the anode, even though the E0 value of the halide ions are more positive. So, if we look at if this is low, then we look at E0 value, because it's not high enough to actually take its place. So we look at the E0 value again. Since we're talking about chloride ions and hydroxide ions, we're going to find where the chloride ions and hydroxide ions are. So here and here. So we have, let me just see, 0.40 and 1.36. So, back to here. At the anode, it will undergo oxidation. So you want to find the easy one. If it the way we find the easier electrolyte that undergoes oxidation, we need a more negative or less positive E0 value. So I'm gonna go back there again and double check. 0.40 and 1.36. So OH minus is 0.40 plus 0.40, and Cl minus is 1.36 positive, if I remember correctly. We want to find the more negative value. Since OH is less positive or more negative, it is a lower value. So OH minus is the one that reacts at the anode. So since at the anode OH minus is less, E0 of OH minus is less positive. Hence, at the anode, it's OH minus that gets reacted. So, for OH minus becomes, I think it was 2H2O plus O2 plus 4E minus. But yeah, that is if we have a low concentration. How about a high concentration? Again, look back at here. Higher concentration at the electrolytes will be discharged. The halide will be discharged, even though the E0 value are more positive. What that means is, I do not care. The cell does not care. The electrolytic cell does not care. It doesn't care that OH minus is more positive, because halide is too dominant there. Halide is too dispersed there. So the anode will choose the halide immediately. In this case, it's Cl minus. So Cl minus gets chosen. Not gets chosen. Reacts, oxidizes, because it has high concentration. So because it has a high concentration, it gets chosen instead. So instead of 4OH minus becomes 2H2O plus O2 plus 4E minus. Then instead you will get Cl minus becomes Cl plus Cl2. So Cl minus becomes Cl2 plus 2E minus. So if it's high concentration, you will Cl minus is the anode punya electrolyte. If it's not concentrated enough, then it will choose the 4OH minus instead. But remember, is it an electric electrode? Is it a halide? If it's a halide, how concentrated? What is the E0 value? So determine what is the so when they ask you to determine what occurs at the anode, what occurs at the cathode, you need to find out what actually goes through them. So if it's solution, right? If it's aqueous solution, aqueous means there's water, which means in electrolysis it will become H plus and OH minus. And then you also have to take into consideration the solution. For example, in this case it's Cu2 plus and Cl minus. But what if I turn this electrode into a copper electrode? Then you also have to consider in the anode that there's another electrolyte there, which is pure copper. Yeah, pure copper. It's not Cu2 plus, it's not Cu1 plus, it's Cu, just Cu. So if it's an active electrode, instead of any of these, you instead will get a Cu becomes Cu2 plus 2E minus. You see how there are 3 different results depending on what type it is. If the electrode is active, like for example copper, then the copper itself would become oxidized. If it's a halide solution, then you must consider the concentration of the halide. If those are out of the way, then you can look at the E0 value, the center electron potential. Okay, the next thing that I want to bring up is the main difference between electrolytic cell and chemical cell, or I think it's called Daniell cell. But before that, I want to mention about the observations, because observations are the second most important thing. First important thing is the cell itself. Second most important thing is what do you see from the erection. So I left out one part, which is since I'm going to consider that this is gas, this is also gas. Okay, if that is gas, I need a tube here. And then it is filled to the brim with water, so I can use water displacement reaction. If it's if it's oxygen gas, if it's oxygen gas, you will see like an electrode like that, and then you see one part is covered. That means it is gas. Gas is collected here. If it's just normal like this, that means one of two things. Either that doesn't mean one of two things. That means one thing. If there is no like extra add-on here, what happens is your thing, your substance here goes onto the electrode. So like for example, over here is copper. So since copper is reduced at the electrode, what happens is the copper sticks onto the electrode. So now this whole part is copper. So you have to consider those observations. The most important ones are you don't only have to consider the observations at the cathode and at the anode. You also have to consider the observation of the solution, for example. What else is there? Any impurities that have been formed. That is for purification of metal. And you think there's anything else? Yeah, there is impurities, presence of impurities. There is concentration of solution. What else is there? Oh yeah, color of gas, color of what is the what is there any insoluble substance? So for example, the most important one is copper. Copper 2 ions are always blue. Okay, copper 2 ions are always blue. That's number one. So if you see like copper nitrate, I think copper nitrate or copper chloride. I think copper sulfate also. I forgot if copper sulfate also works. But yeah, if it is a soluble copper 2 plus ion, the color of the solution will be blue. And how blue it is depends on the number of copper ions. So for example, in this reaction that I just mentioned, since copper is being used to react at the cathode, yeah, I used the wrong part. It's here. Here. Since I use copper ions to react at the cathode, that means copper is stolen from the solution. So what that means is the concentration of copper 2 ions actually decreases. When the concentration of copper 2 ions decreases, the what you have to write is concentration of blue color becomes paler. It becomes less blue. And that's because copper ions are lost in the thing. But again, if we're dealing with copper electrodes, Cu, Cu, and it's the same thing again, it's CuO. So not CuO, CuCl2. Then copper will go here, right? Let's say this is the cathode, this is anode. So at the cathode, copper will definitely go here. So deposited. But what happens to the anode here? The anode actually becomes thinner. So what happens is it will turn slightly thinner, like that, while the cathode will gain some extra substance here. This is because, as I mentioned earlier, the copper anode itself is the one that undergoes oxidation. So what happens here is copper becomes copper 2 ions. So now you have copper 2 ions here as well. So because there is copper 2 ions going in, and there's also copper 2 ions going out, there is no net change in concentration of Cu2 plus ions. If only copper is being reduced, copper 2 ions being reduced, then it will become paler. But if there is a copper anode and copper is being reduced, then there is no net change. So you have to be careful when answering this. And then there's a few gas colors that you have to know, or a few gas characteristics. For example, if you are collecting two gases, so here, let's say here is hydrogen gas, here is oxygen gas. Then you used to remember what you learned in Junior 3. Oxygen gas rekindles a glowing splint. And then this one is the pop sound. So that's how you test for the presence of oxygen gas and hydrogen gas in this thing. Another thing would be what was it again? Okay, so we have the main part, which is copper, and then this one. Oh yeah, chlorine gas. Chlorine gas is greenish yellow. So if chlorine gas forms, like for example in this part here, that means then you have to write greenish yellow gas is formed. Okay, I forgot to mention one thing. In oxygen is insoluble in water, so you would see some gas bubbles. So regardless of going splint, gas bubbles appear. This is observation. This is test for presence. Okay, test of presence and observation are two different things. You cannot see hydrogen, but you can see oxygen. You can see the bubbles going up. For chlorine, greenish yellow gas is formed. I forgot if bromine can become a gas as well. I think Br2 isn't rarely used, but I believe it is brownish red, I think. I forgot already. But the main part here is Cl2. Cl2 always comes out. It's Cl2, Cu2 plus, and oxygen gas. As well as, yeah, I think that's it, actually. And then you have to take into consideration what salts are soluble, what salts are insoluble. Okay, yeah, I think I'm going on too long, but that's really how big the chapter is. Okay, now we're gonna go to the chemical cell or and the electrolytic cell. The main difference is in the chemical cell. Let's draw it both first. Okay, let me just look at the thing again just to make sure that I'm not doing anything wrong. I'm gonna look at. I think I forgot to add one part. Oh no, it depends on the solution. For electrolytic cell, we have batteries here. For chemical cell, we have a voltmeter to measure how much the voltage is. The main difference is, here's positive, here's negative, because the longer one is positive. The positive part is the anode. The negative part is the cathode. Yeah, positive terminal is anode, negative terminal is the cathode. But however, for this part, let's say here's the anode and here's the cathode. If here's the anode, then this part is negative and this part is positive. So that is the main difference. In electrolytic cell, the cathode is the negative terminal, but in the chemical cell, the cathode is the positive terminal. So you have to be careful with what this is and what this is. Let me just see if I can find a question to prove my point. Okay, if you go to page if you go to page 27, I think, I believe that shows this part, the page 27, where you see it says there, positive terminal is cathode, negative terminal is anode. But if you were to go to the 1.2, I think, about electrolytic cell, I think it's after that a bit. Yeah, electrolytic cell. If you were to look at the thing, the positive terminal is connected to let me just see if I can find it. Yeah, if you go to page 39, the positive terminal is connected to the anode, and the negative terminal is connected to the cathode. So okay, so that's one part. Another thing that I want to bring up is this can exist in multiple ways. For example, for this one, I mentioned earlier that it can either be like that, or if they're collecting gas, then the cathode, this is the anode and the cathode, they will be enclosed by this test tube, I think. And this test tube is used to collect the gas. And then for the chemical cell, there are multiple types of chemical cell. They can either share the same solution or they have to be in separate solution. I forgot the reason why they have to be in separate solutions. I mean, I'm not so sure why. But if they are in separate solutions, you'll see something called a salt bridge. So you see a salt bridge, and then Oops, my bad. And then you see an electrode here. Another thing is these two electrodes have to be in different metals. For here in electrolysis, they can both be copper. But for chemical cell, one has to be for example, here is zinc, here is copper. It cannot be both copper. If not, then it wouldn't work. And then the solution has to contain that substance as well. For example, in zinc solution, for example, in zinc electrode, your solution has to contain zinc. For example, zinc sulfate. And then for copper, it has to be copper sulfate. Okay. And then you might be wondering, how do I know? Like if it's about this one, you can see the battery. But how do I know which one is cathode, which one is anode? That's why I brought up the standard electrode potential again. So I have my book next to me. Zinc is negative 0.76 volt. And copper is plus 0.34. So remember, the more positive is reduced, and negative is oxidized. So since zinc is more negative, zinc undergoes oxidation. Since zinc undergoes oxidation, zinc is the anode. Since copper undergoes oxidation, the reduction, then here is the cathode. So yeah, you need to be careful on these types of questions. Chemical cells are very confusing, and they do not just exist in this way. They can also exist in a way where it is like in a porous pot, and then yeah, this thing is very confusing. Yeah, it can also exist like this. It can exist like this. It can also exist like this, I think. I believe this is also I remember seeing in one page. I forgot what page it was. Yeah, page 9. That is also a chemical cell or a voltaic cell. So yeah, it can exist. Chemical cells can exist like normal, like this. They can exist in two separate solutions. They can exist in the same beaker, but still two different solutions. And it can also exist in this tube thing, U-tube thing. But then they all share one similarity. The whole thing must conduct electricity, because the difference between chemical cell and electrolytic cell is, in electrolytic cell, the battery is the thing giving the electricity. In the chemical cell, it produces its own electricity. So in this one, let me just see if I can find the page again. Oh my god, I hate this. I hate going through all the pages, but that's how hard this chapter is. So yeah, the main similarity is the whole thing must be salt. This is salt. This is salt. This whole thing is salt. This is salt. This is salt. This whole thing is salt. And number two, the salt substances must be connected to each other through a way. So this one is straightforward because they're all suspended in the same solution. But for this one, this is a salt. A salt tube. And this salt tube allows it so that when this thing undergoes oxidation, it loses electrons. It loses electrons. So when it loses electrons, the electrons travel all the way to the voltmeter, go all the way down, and then it will continue traveling. It will go all around this tube, and then it will go back. So this salt bridge must conduct electricity. That's why it has to be a salt bridge, because salt conducts electricity. And for this one, it is covered, and then I want to conduct. How would it get through? It can go through because this is actually called a porous pot. A porous pot is a pot that has some holes. So the holes aren't that big, so it wouldn't actually cause the solution to be completely mixed up, but it allows some space for the electrons to go through and then continue going around the cell. And then similar here, this is the solution itself, and then this is your salt tube. I forgot what it's called. Just check again. Your salt bridge. So in this case, oops. Here, this is your salt bridge. This thing. For here, this is your salt bridge. But they do the same thing. They allow for the electric current to go all the way from here back to the cell, and then it'll keep going round and round and round. So it'll be a complete circuit. For electrolysis, it will disperse. The chemical cell itself produces its own electricity. So the battery itself makes its own electricity, but for the chemical cell, it creates its own electricity. It doesn't need the battery to help it. Okay. I think I would love to go on about more,